everyone. First, I'm just going to start by saying that if you don't work harder, you got to work smarter. So that's why I'm working with all these people, my collaborators. They're great people, and I could not have done many of these things without them. So I was asked to talk about repeating nuclear transients. I'll just start with a little bit of an overview. We've heard a lot already about QPEs. We've heard about periodic, longer-term transients, but maybe not necessarily about everything. After that, I'll kind of try to convince you that all these lines of evidence are emerging now that these are probably, maybe, part of one not so big happy family. And I'll try to convince you whether that is the case or not. So we've seen these figures several times. We all know that there are these QPEs, repeating phenomena on timescales of less than a day. Whether that's physical or not, we'll leave it out there in the open. So if you plot this just on a simple recurrence time peak luminosity diagram, then they populate this area here below periods of a day. But there are many other things in galactic nuclei that we have seen repeat over time. And this is just kind of a flash of all the different light curves in different bands that we've seen of things that have repeated and are located in a galactic nucleus. So we've seen this picture several times. SM14KO is an optical transient. There are several sources. IC3599, we heard from Richard. This source here, RxJ1331, published by Adam Maliali et al. So these are things that are recurring on timescales of 10, 20, even 30 years. And so it's really important to keep monitoring the sky in as many wavelengths as possible in order to detect these transients. So it's not easy to discover them. If you just look around a bit here, you have sources which recur on a timescale of 20 days, and then you have several spectroscopically classified TDEs that seem to recur on timescales of several hundred or roughly 1,000 days. And then you just have like other weird sources, this Rosetta source, of which we've seen 5 cycles. So all super interesting. I noticed that 2018 FIK is no longer among this list. So we'll have to add it again because I have a slide on it. Right. So if you put the recurrence timescales and peak luminosities of these other things on here, you get this kind of jumbled thing where it's not really clear what is the relationship between all of these. But kind of fundamentally, these are things happening in galactic nuclei, and so they are most likely the result of many-body dynamics in these chaotic and dense environments. So Muriel wrote a very nice paper where he kind of compared some of these properties of QPEs and what he called repeating nuclear transients. So those are the longer-term systems. So we've already mentioned that the timescales seem to be quite different. All QPEs are soft thermal in the X-rays. Not all recurrent nuclear transients have X-rays. And even if they do, sometimes there is a corona, sometimes there's only a corona. There has been a big question mark about is there any UV optical emission from QPEs? And so we heard from Wenbin that there should be a counterpart, but then we heard from Itai that there shouldn't be a counterpart. So after this talk, I'll start taking bets on who is right. Just to say that we are looking into this, so we took HST data of a QPE contemporaneous with XMM. I have the data, I just haven't had the chance to fully reduce it yet, but so we are already in a stage where we can start to really test these predictions. This is another kind of emphasis of QPEs seem to be like this very well-defined little class of objects, while these repeating nuclear transients are decidedly not. You have some spectroscopically confirmed TDEs that have rebrightened once. So they have both UV optical and X-ray transient emission. Then you have SM14KO, which kind of is the same, but then it doesn't really look like a TDE spectroscopically necessarily. You have some rebrightening supersoft X-ray sources that show no UV counterpart. And then you have these quasi-periodically repeating transients, this Rosetta source and this Swift source that also don't seem to have a UV counterpart. So there's a lot of heterogeneity in this second group. So you could ask the question, well, is this all, are they even part of the same family or not? So it's not quite clear. So just kind of to emphasize, all this variety of observations that we have. So for example, for a source such as this, it has rebrightened in the X-rays, but we don't really know much else. So it's really difficult to classify that properly. So just like one slide on 2018 FIK, which is a TDE which rebrightened after about 1,200 days after the first peak. And so in this partial TDE model that where Eric did a lot of the numbers, and we predicted that there should be another turnoff 1,200 days after this turnoff that we saw. And so this is just like a preliminary plot, but so you can see this is around 700, and sure enough, around 1,800 days, we are seeing this decline again. So that model is still out there and still working. So thinking a bit more holistically about this, how can we better understand the samples of nuclear transients and what binds them together? And so we've heard plenty about theoretical models that link together QPEs, TDEs, and partial TDEs. Some people would say that we already have the evidence that we need, because we have this GSN 69 source, which is, I call it a photometric TDE, because it only does stuff in the X-rays, which is not the typical thing that we see in UV optically selected TDEs. But what we really would like to see is a spectroscopically classified TDE that then, after some time, starts showing QPEs. And if you want to hear more about that, I would not leave early in this session, is all I'll say. But what I want to talk about is a different way of exploring this question by looking at the host galaxy properties of both TDEs and QPEs and see if we can find any connections there. So we already know that TDEs really like post-starburst galaxies. They are overrepresented by a factor of 20 to 100, and we know that the same is true for QPEs. So what else can we say? So we know that TDE hosts, some of them show these very extended emission line regions. These are two literature results for SAS14 Li, published in 2016, where this is you have this ionized gas clumps here, very patchy, on scales of 10 kiloparsecs or so. This is a post-starburst galaxy. Decker found another one that shows a similar extended emission line profile in manga data. This is also a post-starburst galaxy. And so what I did then is I looked for all the MUSE data on TDE host galaxies. There are 16 sources for which there is data. Just to put that into context, every MUSE cube is about 100,000 optical spectra. So this is 1.5 million optical spectra that we're analyzing here. And so we found another extended emission line region source in the host of IPTF16FNL, also a post-starburst galaxy. So you see the continuum image in grayscale here, and so in the continuum this looks like a perfectly normal elliptical galaxy. If you look in O3, then you see these contours, these white contours here are an extended emission line region, and it's kind of difficult to see, but you have patches of gas here and here as well. So that's about 6 or 7 kiloparsecs away. So you can try to figure out, okay, what has ionized this gas, or what is it doing there? So you just measured line ratios, put it on a BPT diagram. The red here is the nucleus, so you can see it there. So it's AGM photoionized throughout, essentially, this emission line region. The nucleus is probably a liner, and this may be because this is post-starburst galaxy, and therefore we have to correct for stellar emission, and this is, there's some uncertainty there. But certainly the outer regions, are clearly photoionized by something that is not a stellar continuum. Then by assuming that these lines are powered by recombination, or are set by, that the line strength is set by recombination, you can calculate from the line strengths that are observed, what is the nuclear luminosity that you need in order to power them. And that is what you see as a function of distance in this plot. And so you see that the furthest emission line regions, so the furthest regions of this region, give you the best constraints. And so this is telling us that there must have been a source in the nucleus with a luminosity of at least 10 to the 43 ergs per second, 15,000 or so years ago, for several thousand years. And this is a lower limit. And so then, this is true for every TDE host galaxy with an emission line region. It is true that the nuclear luminosity that we see currently is insufficient to power this. So the nuclear luminosities are lower than these limits, essentially. So either there was an AGN and now it has faded, or maybe there was just a burst of TDEs that kind of powered all this gas that was floating around in this galaxy. That's something that I'll come back to later. If you look at the kinematics of this gas, it's doing very weird stuff. On the top here, you see the kinematics of the stars. So you see this nice rotational motion in the stars. This is the velocity dispersion. So you see that it kind of peaks in the nucleus and then kind of goes out to lower values. If you look at the gas, however, it is all moving in the same direction. So the gas here is not following the stars at all. And if you look at the velocity dispersion of this gas, then you see that it is high in the nucleus, similar to the stars. But in this emission line region, the line widths are lower than 50 kilometers per second. And so this is very weird. There is no turbulence whatsoever in this gas, which means that probably it is not, the kinematics are not AGN driven, because you would expect to see higher line widths. And it's also incompatible with shock ionization of this gas. You would also expect broader lines. Okay, so just kind of as an overview, we have 3 out of 16 TDE hosts for which we have constraints that show these emission lines. All 3 are post-starburst. And there are a total of 5 host galaxies in here that are post-starburst. So you can compare that to other samples of galaxies. Decker did this very nice study of post-starburst galaxies in MANGA data, and she found that around 5 or 10% of these have a similar extended emission line region. And there are also other studies of larger samples that find similar fractions. And so this is a factor of 10 overrepresented compared to normal post-starburst galaxies. So even within this preference of post-starburst galaxies, there is this very specific post-starburst phase where the AGN has faded. There's a lot of gas around, and it's photoionized, but not really doing much. That seems to be preferred by these TDEs. And so in absolute numbers, you're talking about a factor of 10 less than the typical post-starburst incidence, so that is a very small number of the total galaxy population. So you can kind of do a back-of-the-envelope estimate of what would it take in terms of the TDE rate that you need to power such an extended emission line region. And I'll walk you through the numbers here. So the typical region visibility is about 15,000 years. So we scale that by the incidence, 3/16, so you get this nuclear engine duty cycle or so that you see, thank you, of 80,000 years. So you need a source with a luminosity higher than the minimum luminosity we inferred, 10 to the 43 ergs per second in this case, for 80,000 years. So then you have to make some assumptions on what kind of energy can a TDE put into its environment. So we took some broad assumptions. All TDEs can provide a luminosity more than 10 to the 43 ergs per second for roughly 100 days or so. And so let's say that we require them to be X-ray bright in order to power this non-stellar line ratios. We have some fraction here, and then you get these numbers out. So for a random galaxy, you would need a very high TDE rate. For a post-starburst galaxy, this is kind of, this is still on the high end of what is observationally inferred, but this seems to be borderline, I would say. But some of these assumptions are actually very conservative. If you assume that you don't need X-rays, you just need a hot EUV source to ionize these photons, then you can get away with a factor of 3 already. If the disk lives for 1,000 days rather than 100, you get a factor of 10 and so on. And so you can get kind of numbers that are well within range of the observational rate of TDEs in post-Starburst galaxies. So what about QPEs then? Here are 3 Muse cubes of QPEs, GSN 69, QPE2, and RxJ 1301. And sure enough, you can see this green here is, I think, nitrogen-2, so ionized gas. And so you can see also in 3 out of 4 QPE sources. Now here, okay, it's a bit difficult to see. I hope you can see this. There is faint ionized H-alpha emission right here. Here, the continuum in red, and you see this complete, train wreck of a galaxy in ionized gas. So, 3 out of 4 is very similar to 3 out of 5, and a lot higher than the 10% or so that of incidence that we see in typical galaxies. So my reasoning here is that, okay, it seems like there is some kind of connection between these systems through their very peculiar preferences in the host galaxies. And you can look at all the same things, the gas kinematics of these systems. This is GSN 69. So you see again that in most of this emission line region, the turbulence is very low. The line widths are of order 50 or so kilometers per second. So this is all very, very similar. This is a plot of the gas velocity relative to the stars. And so you can see, here you have blue on the left, red on the right, which is motion. Stars here are coming towards us, and here they're going away from us. And in the gas, relative to the stars, this is reversed. So the stars are doing something, but the gas seems to not really care about it a lot. And this is a different one where the line widths are even more extreme. So the line widths here are less than 30 kilometers per second throughout all of this galaxy. So that is very weird. You can do the same calculation again for the ionizing nuclear luminosity you need in order to explain these. And so these are preliminary plots where the inner part here to the left of this red line, that is the actual galaxy and its star forming, so you can kind of safely ignore that. But you can see, you get pretty similar limits on the luminosity, so a few times 10 to the 42 ergs per second for, I think this is GSN 69, 10 to the 42 or 2 or 3 10 to the 42 ergs per second for the other 2 galaxies that you see here. So this is, again, all very similar. I haven't had the time to do the same kind of calculation of whether QPEs could power these ratios or if that just doesn't work. And so if you have opinions or thoughts on this, then I would be very happy to hear about them. Just to say that you can calculate the present day luminosity of the nucleus, and so these are kind of marginally still consistent with each other, but I haven't had the chance to correct for star formation, and especially in these 2 cases. That will probably bring down this number in red by quite a bit. And so the chances are very high that also in all 3 of these galaxies, we will have to say that if there was an AGN, that it has now considerably faded compared to its previous luminosity. So we can really map out the accretion history of the nuclei of these galaxies. So, QPEs and also TDEs seem to prefer these very gas-rich, probably post-merger environments, is kind of a main takeaway. And so then the question, of course, is why? What is going on here? And so this is an invitation to everyone in the audience that has their model, to kind of explain to me and everyone else to help us understand whether this provides any good constraints on the lifetimes of QPEs, for example, whether that is compatible or not. So there could be, selection biases, where we see faded AGNs, so we don't see TDEs in faded in AGN systems just because of the spectroscopic classification bias. And similarly, QPEs, you may not see them if you have an actual active AGN, so similar to what Giovanni proposed for GSN 69. I'm running out of time, so I'll just kind of give a brief summary. So we have these nuclear and repeating transients that are happening on a large time scales, a large range of time scales. Some of them, we call them QPEs, others we call them partial TDEs, and so on. Their properties are heterogeneous, but it seems that their host galaxies share some very specific phases or preferences. And to study this further, we are still getting data of all the remaining nuclear repeating transients as well as the new Rosetta QPEs. So we will have a complete sample of IFU data for all of these host galaxies where we can kind of study this further. And thank you, and I'll take questions.
Quick question. So Erica, maybe obviously a question for Erica as well. I'm not sure if I can see run on here. Okay, great. So Erica looked at about, I think, 14 ZTF TDEs, including a particularly interesting one with KCWI, and didn't see any emission line regions. So if you include those plus the new sample, would you say that TDEs specifically are not overrepresented in extended emission line regions?
That is a good question because so it's also a matter of sensitivity.
Yeah.
And so KCWI has a lot higher spectral resolution.
Yeah.
But the pixels are a lot larger.
Yeah.
And so you're a lot less sensitive. So yeah, it is difficult. So yeah, it's difficult to compare different data sets and draw like a proper conclusion from that. Yeah. But it's something worth thinking about.
It covered the galaxies. Yeah. Yeah.
But these are outside.
That's fair. That's fair. That's totally fair. Like,
we should overlay the KCWI field of view on these.
Oh yeah, it's
because
tiny.
it might be outside.
Yeah.
Yeah, that's totally fair.
Yeah, good point.
I'm just curious about the other 13, what you can tell us about them.
Oh, nothing. I haven't looked at them.
Okay.
It's a million spectra. If you want to look at it, you're free. You're free to do so. Yeah.
Yeah. So I have a question about how you get the. So in one of your slides, you're showing that for a sufficiently high TDE rate per galaxy, the TDE themselves are able to ionize and power the extended emission line region. How do you get the? Can you go back to that slide? Didn't get how you estimated the TD. Yeah, here. Yeah.
Right.
The 1,000-day case. Let's say I think 1,000 days is not too bad.
So
yeah, it's a far UV for 1,000 days, so it's 3 years.
Right. Yeah. So this is based on what Short has shown, that you have these very long-lived and very hot accretion disks that can give you quite a bit of energy.
Let's say in that galaxy there's 10 to minus 3 per galaxy per year. So every 1,000 years there's one TDE. So that TDE is enough, but it only lasts for 3 years, right? So 1,000 days.
Right. So this is the number that you would need in order to explain the extent of this emission line region. So this is not, so if you have less than this number of galaxies, of this number of TDEs, then you cannot power the emission line regions that we see. That is the...
You mean the size or the energetics?
The energetics, yeah.
Oh, you're only putting in the energetics.
Right.
But then there's a TDE FUV light are like 3 light year shells, right?
Right.
Separated by
yeah. So then the assumption is that you're doing this for 15,000 years. That's an assumption.
Oh, there's sufficiently dense shells.
Yeah, exactly. Yeah.
Yes.
I mean, yeah, this is just the back of the envelope.
Just the energy is enough.
Yeah.
That's amazing. So if these rates are possible, I mean, some of the calculations looks like, so the TDE themselves are able to power the extended emission line region.
Yeah, so in some cases, so it also depends. So you have to assume something for the minimum ionizing luminosity, right? Mm-hmm. And so in some galaxies, this can be 10 to the 43.7 or 8. And so then you have a correspondingly lower fraction of TDEs that would be bright enough to contribute to that luminosity. And so This also depends on
Yeah,
that.
during when the TDE is on, only lasts for 3 years, that luminosity is high enough. But then for the rest 900 years, the TDE is off, right?
Yeah, right. Yeah, so that is
You
not
worry about the
taken into account.
recombination.
Right.
And so
Yeah,
on.
we can talk more and try to figure out how to do this
Thanks.
better.
Questions for our speaker? If not, let's thank Thomas again.